right. Just thank you all for being here today. I'm very pleased to introduce Dr. Paul J. Ferraro. He got his undergraduate degrees from Duke University in biology and history, where he also got a master's with a concentration in environmental economics, and has a PhD from Cornell's Applied Economics Department. Now, Dr. Ferraro is the Bloomberg Distinguished Professor of Business and Engineering at Johns Hopkins University, where he holds joint faculty positions in the Whitting School of Engineering and the Carey Business School. His research focuses on behavioral economics and the design and evaluation of environmental programs and environmental areas, both public and private sectors. His focus on applied and multidisciplinary research brings him to collaborate with scientists and engineers from a variety of social, natural, and physical science disciplines and practitioners in the field. So without further ado, I will pass to Paul. Thanks.
Great. Thanks, Joe. So I don't know if all of you know, but I've been here for about a day doing lectures. So I think this is the fourth lecture. I'm getting tired of hearing my voice, but I'm glad to see everybody's here and some more folks are here. We've been doing an immersion in behavioral science and causal inference. And this seminar is going to touch on both of those topics. And I wanted to focus on the bigger picture that I'm looking at here, that we're looking broadly at the issue of resource-conserving technologies. So I did a presentation yesterday on economics and how economists think. And when economists think about undesirable behaviors that lead to costs for the environment, so using energy and water and polluting and pesticide and nutrient applications, economists, 90% of them think we should just raise the price and make it more expensive to use water, to use energy, to put pesticides and nutrients on the land. So 90% of everybody else thinks that's a dumb idea. Right? No one thinks that we should raise the price of these things. We're looking for other solutions. And one of the most popular ones is technological fixes. If we can make farmers use inputs more efficiently, if we can make households use water and energy more efficiently, we don't have to raise the price of these activities. People will use less water, they'll use less energy, farmers will apply fewer pesticides and inputs, and they'll also use less water, and we'll get a win-win for the environment. Right, so we've got energy efficiency technology, water efficiency, precision agriculture. In developing countries, you have cook stoves, fuel-efficient cook stoves. We've got fuel-efficient cars. And the idea is that we can achieve our development and environmental goals through efficiency. And we don't have to go through that painful process of making it more expensive to do these activities that have impacts on the environment. And you'll see a lot of these points being made. This is good for the economy and good for the environment, and therefore you get one of two arguments. You get one argument that is that businesses and consumers are dumb and they're missing all this opportunity to save money and save the planet. And then you have some other people who say, well, it may not be financially profitable at the individual level for a business or a consumer, but it's socially desirable to do this, and we should subsidize the adoption of these technologies and innovations in these technologies. And in the water context, water efficiency is sort of a mantra. Any attempt to deal with water scarcity, whether it's current droughts or for climate change adaptation, has to have water efficiency as part of the solution. And so if you look at California, which has been going through a lot of droughts, recently, I'll skip that one. No, I guess I'm not going to skip that one. Let me go back to this one. So even in developing countries, there's this idea that if we promote efficiency, we can have the developing countries go in a different trajectory, that they won't be using energy like high-income nations or water like high-income nations, that they'll be much more efficient with it. Fuel with stoves will not only make it better for the women, they don't have to go far to get the fuel, but it'll be good for the forest because they'll reduce the amount of fuel they actually need for those stoves. So in the water scarcity arena, there's increasing focus on drought-prone areas, and it's only going to get worse with climate change. And some of these areas are in the poorest regions of the world. and efficiency is being promoted as one of the solutions. Not raising the price of water, which could be very damaging to poor households who already have trouble struggling to meet their current needs. So there's this hope that if we can somehow get better technology into those areas, we can solve the environmental problems without having these poor development impacts. And like I was starting to mention, even in California and high-income nations, California has a climate change adaptation strategy that's getting a lot more attention with all the droughts in the last 6 years. And one of their key pillars is aggressive attempts to get efficiency in agriculture, in business, and residential households. And when you ask, well, how do we know that efficiency is a solution to these problems? What's the evidence? It largely comes from engineering models. Models that say, okay, we know how this technology works. We know what the status quo technology, how it uses water or energy in any other field. And we just switch the technology. And what they often don't switch is the human behavior of the people adopting it. And they have this assumption that humans will take this new technology and do what they were doing before. Farmers will adopt the new irrigation technology and farm exactly the same way they were doing before. In fact, they do this on agricultural stations when they test new technologies. They randomize the technology on plots, but they make sure that they're doing the same crops, same area, same everything on those parcels, and then they see what the difference is in water consumption to get a particular output yield. And that's fine for just testing the performance of the technology, but as we talked about yesterday, economists assume that people are trying to do the best they can. And when they get new technologies, they tend to re-optimize, change their behavior in ways that we need to understand. The other approach to measuring the effects of efficiency on resource use or environmental outcomes is to do naturally occurring data. We look at people who adopted the technology versus people who don't. And we talked about earlier on the lecture on causal inference, it's really hard to use non-experimental data to draw causal inferences because there's so many other rival explanations that could explain differences in resource use between those who adopt a new technology and those who don't. You have to ask the question, why are some farmers adopting precision agriculture and others aren't? Why are some households adopting high energy efficiency appliances and others aren't? And are those reasons also likely to affect energy use? So what we're picking up is not the effect of efficient technology adoption, but the underlying characteristics of the people who adopt it. So just to clarify again, with the engineering estimator that's out there, it's really simple. I'm in an engineering department. People often ask, is this true? Is this really the way it's being done? Yes, it's the way it's being done. Where they'll just take the shower head, something really simple. You got an old shower head, 15 liters per minute, new shower head, 7 liters per minute. I use 10 liters per day to shower with the old technology. I'll use less than 5 liters per day with the new technology. Simple, assumes no behavioral change when we do that. And how do we get some of that information on what people use? We do it lab performances of the technology. Sometimes they might do field performances of the technology. They use secondary data, primary data, but the underlying assumption about no behavioral change. Or in the best studies, you get a very stylized behavioral change. Like the Global Environment Facility assumes with energy efficiency technology that 20% of the gain will be taken back through a rebound effect. Where does 20% come from? It's complicated, but it's not the best of evidence, and it's just a sort of stylized behavioral change. It's not based on actual observations. So I'm broadly interested in a bunch of research questions that I'm going to focus on in the context of water efficiency. So the first one is, does it work like the engineers say it does? Right? Are their models reasonable approximations of the impacts of these technologies? And the other one we're interested in, because I'm going to have training in economics, is are consumers and businesses leaving cash on the table? Meaning there's often this argument that these are win-win. The people who adopt it win from lower costs, and the people who want to use the water, breathe the air, or whatever the other resources are, the externalities are, they benefit as well. Benefit for the environment and for the people. And this is a puzzle to economists, like we talked about yesterday. How is it that businesses who are ruining the environment, trying to make a profit, as they're often characterized by environmentalists, are leaving huge amounts of gains on the table because they won't switch their lighting, or they won't switch the agricultural technology that they're using on the farm. Seems hard to believe, but it's possible that we talked about some behavioral anomalies and things like that yesterday that could cause that. This is the example that many of you have seen from the energy context that McKinsey did. It's a famous curve showing the costs of adopting different technologies that can reduce greenhouse gas emissions. And the thing that puzzled economists was the beginning of the graph with all these technologies that are well known that have negative costs, meaning that if businesses adopt them, they'll actually earn money, or if households adopt them, they'll earn money. And everybody out of this is that we can do all this to save the environment and people will be better off financially. But to an economist, it just seems really odd. How can all this money, this cash, is sitting on the table and they're not taking it up? Like, what's happening here? Is it some imperfect information, as people often argue? Is it just cultural recalcitrance? People just are not used to doing it that way and don't want to change? Or is it that these calculations are just wrong in terms of the inputs that went into these economic calculations? Those are just wrong, that there actually are positive costs, that we're just missing it somehow. So do they work? Are people leaving cash on the table? I'm going to skip that. And then the issue is, even if people aren't leaving cash on the table, it may be that this is an efficient way to achieve environmental outcomes, that we should be subsidizing these technologies. Right? Should we actually use this as a cost-efficient way to get certain environmental gains? Right, so the few studies that have been done on energy efficiency are mostly in energy. They're mostly observational, meaning non-experimental, meaning it's really hard to figure out if you're measuring a causal effect. And most of the effort goes into this rebound effect, this idea that when I create greater efficiency, I'm lowering the effective price of driving, of cooling my house, of heating my house, of putting fertilizers on or pumping water onto my fields. And therefore, when we lower the price of something, we increase the quantity demanded. Basic economic law. And so what happens is you get a more fuel efficiency in the refrigerator, and people take back some of those gains with bigger refrigerators. I'm trying to get this picture of my mother standing next to a refrigerator at the age of 13, and the refrigerator comes up to her armpit, right? And so the refrigerators now are so much more efficient, but they look like that double door monster that's out there in the cocktail lounge room. We've taken back a lot of those gains in more cooling, more space. And there's almost nothing from middle and low income countries and nothing from experimental design. So we're going to try to solve some of those problems. And the other thing that I'm going to talk just briefly about today is this issue of disadoption. So anybody who works on fuel cook stoves knows that disadoption is a huge problem. But engineers in general assume that their technology is great, people adopt it, and don't disadopt it. But in a lot of contexts, disadoption is a huge problem. And when you point it out, there are generally two arguments for why people disadopt these technologies or practices that environmental scientists promote. It's because when they first start doing it, it is costly. They're getting used to this new thing. But after a while, those costs go down. They form habits. Farmers get used to the riparian buffers. They get used to changing this irrigation technology, and it's not so costly anymore. So if you can just get them over that hump, they're more likely to stay with the technology and not disadopt it. And others say that sometimes people are skeptical of the benefits. You know, this energy efficiency, is it really going to save me the energy cost? They use it for a month or two, these lights, I'm not sure they're really saving me any money, they disadopt them. And if you could just get them to use it for a period of time, they'll see the benefits and then they'll stay with it. And so we're interested in trying to look at that in the water efficiency context of disadoption. And I'll talk about how we do that later. All right, so I want you to just think again about the shower head, the water efficient shower, because it's a really simple technology for everyone to understand. And this is how people tend to think about the impacts of adopting water efficient technology, is this simple change in the performance rating, assuming no behavioral change of the participant. But I want to argue that there are lots of potential behavioral mechanisms through which people will change their behavior after adopting a low flow shower head. So the first one, we talked about this before, rebound effect or take back effect. This idea you've lowered the effective price for bathing, and it doesn't have to be the shower head, washing, cleaning, watering, irrigation, and that can make the savings bigger or lower depending on how that rebound effect works. But generally, it makes it so that the savings are much lower than the engineers assume. Right? There's a much take back. There's been one paper showing how you can actually get an increase with some strange sort of rebound effect. But generally, people think about it as reducing the savings you get from efficient technology. People take it back. Farmers adopt a new irrigation technology. Next thing you know, they're irrigating more land, and they change to more water-demanding crops. Right? So that's an example there. Rarely do we change only the attribute of efficiency when we change technology. Often other attributes have to change as well. You change the light efficiency, you change the quality of the lighting. Anybody who's had compact fluorescent lighting compared to incandescent knows you've changed more than just efficiency when you change that bulb. And that may make it more desirable or less desirable to use that product, and therefore change the kind of savings you get. There's a lot of arguments that Priuses actually don't get the big effect that you would normally get because the dashboard is so entertaining. People love to go out and drive that car. There's other arguments that say that some of the other sports cars that are hybrids don't drive as interestingly as the conventional versions, so people drive them less. But all this is anecdotes. But this is a possible behavioral change after adopting the technology. Some people are already conserving water, right? And they're doing it to be good for the environment. And when they adopt this technology, it may change the way they want to express those pro-social preferences. It may make them more likely to want to conserve now or less likely. And it might depend on how visible the technology is to others, about how it changes their behavior. And a related behavioral effect that we treat separately, because psychologists are sort of vague exactly on what this is moral licensing. But this is the idea that, well, I've installed all this new technology, I'm doing something for the environment, now I don't need to only do half loads of dishwashers or half loads of washers, or full loads, I should say. I don't necessarily need to do full loads of the dishwasher, full loads of the washer like I did before for conservation, because now it's more efficient. I put in a whole bunch of energy efficiency bulbs outside my house. I used to always turn the lights off when I went to sleep for energy savings. Now that they are really efficient, I leave the lights on for safety purposes out there. Right? So it's a sort of moral license. I don't feel so bad about it anymore. It's not a take-back effect. It's just that I feel like I invested in these $50 bulbs that use almost no energy at all. I can afford to use a little more energy now for my own benefits. Some of these technologies are very salient. We talked yesterday about how people have difficulty keeping all the decisions in their head simultaneously, that what's salient or what primes them can matter in terms of their decisions. A shower head is something I see every day. It reminds me, why do I have this funky looking shower head? Oh, to conserve water. It reminds me of conserving water, and that might spill over to how long I take a shower or what I do elsewhere in the household. Whereas insulation in the walls, I've done that, it's gone, I don't see it anymore, it may not remind me about energy conservation anymore. Sunk costs, all right, so to an economist, how much I just spent on this newfangled shower head shouldn't influence how I use it, right? Because that cost is sunk. Now all I care about is what are the benefits and costs of using this new technology. But there's some psychological evidence that suggests that sunk costs actually affect my behavior, where I say something like, I just spent $50 on this shower head, by God, I'm going to save some water. And I start turning off the shower early because I feel like I spent so much money on this technology, I need to get my money's worth. Right? That's not an economically rational response, but there are some evidence that people do this, and it could increase the savings that people might get. Another big one that engineers understand but rarely take this into account is that when I see on my low flow shower head or my toilet what the rating is, or the SEER rating on my energy efficiency appliance, that's tested under very controlled conditions that often do not match naturally occurring conditions. Right, so for water efficiency technology, it's under a very high pressure with water that's distilled with no sediments or anything else in it, and is run for a certain amount of time. Right? And we're starting to realize that real performance conditions and lab performance can be quite different. In fact, it's not surprising that manufacturers lobby for particular standards that make their products look particularly good in terms of performance. And then we talked about disadoption as well. Engineers tend to not go back a year later and see if anybody's still using the technology. They assume that once people adopt it, they continue using it And they also don't think about partial adoption. So there was a study that tried to put in these in-home displays to improve energy efficiency in households in Connecticut. And the engineers came up with their estimate based on, well, we're bringing in an expert to install these, they'll install them. It turned out in 70% of the households, they could not install them to the factory installation requirements because of funky things about the house, the electricity. So there really wasn't the installation that the engineers were assuming that would be done in that particular household, which might affect the performances of those technologies. And so just a side note, just to point out, so I have those mechanisms, multiple different mechanisms through which you might not get the engineering estimates of the impacts from efficiency. And therefore, when we think of the impact of technologies on resource use, it's got to matter how we're inducing that adoption of technology. Right? So are we doing it through taxes and fees that make people want to get the technology on their own to avoid those taxes and fees? Are we doing it through information and moral suasion? Here's how much you can save, and this would be really good for your community if you would do that. Are we paying them to adopt it? Are we forcing them and saying you no longer can use incandescent bulbs, you have to use these CFL bulbs? Right? Those are going to affect those mechanisms in different ways. I'm not going to feel much about pro-environmental preferences if you force me to use it. Whereas if I voluntarily adopt it, I may feel like I'm doing something for the environment. It may have something related to my identity. So it actually might matter for the impact how we induce the technology adoption. So in my particular experiment, we're going to do it through giving it to people for free, but it's going to be voluntary. So we can try, because we think that will have the opportunity for most of the mechanisms to be operative, and we don't have the ability to randomly force some people to have a standard and other people not to do it. I just want to mention, I'm going to be focusing on the engineering estimate as the benchmark through which we're going to compare what the real impact is through an experimental implementation. But what typically gets done in the literature to measure the impact of technology adoption is often before, after. So before, this is how much they use. After, this is how much they use. Rarely controlling for things that are also changing at the same time, before and after. Last year they used this much water, this year they used this much water, but lots of things have changed. Temperature, rainfall, the economy, what people are doing inside or outside of their homes. Then there's more fancy things that people do, difference in means estimators, adjusting for trying to observable differences between the adopters and the comparison group, or panel data. We have repeated observations before and after for both adopters and non-adopters. There's not a lot of strong evidence that these observational designs can replicate what experiments do, with randomized controlled trials do, in terms of they give you the same estimate. There's lots of biases that are possible here. And we haven't done the analysis yet, but we have non-experimental comparison groups with which we're going to apply these estimators and see what answers we get from our project. All right, so I've been talking indirectly about the project. What's the project? Project is in Central America. It was in Nicaragua, Honduras, and Costa Rica. I'm going to focus on what we did in Costa Rica. It was a climate change adaptation project working in the driest areas that are very drought prone. Climate modelers saying it's going to become even more drought prone. And engineers saying one solution here is to get these households to be more efficient in their water use. They're extracting groundwater. They've got really inefficient technologies. We've done estimates of what they could save, and it seems to be cost effective for both the people and for the social good. So there was a whole bunch of communities surveyed in 2013 about their water use. So we had data on these communities. We selected 9 at random to work in who had meters, because we had to be able to measure what water outcome they were using. That they had variable water pricing, meaning that people could actually save money if they reduced their water use. Whereas if it's just fixed, then there's no savings at all from reducing your water use. And the communities were actually interested in having us come in, which most of them were in the ones that we approached. All right, so on the left are what they have now for technology. It's this really old technology or nothing at all. It's just a pipe, and the water just flows out of there. On the right are the technologies we were trying to install. Low flow, faucets, shower heads, in the kitchen, in the bathroom. We weren't doing toilets because no one believed that would be cost effective. So we didn't want to test something that engineers said right off the bat won't be a cost effective way to save water in these. And there's actually, not everybody has flush toilets in the homes anyway in this area. So the idea would be at random to switch entire households from old to new technology and compare how their water use changes compared to the groups that don't get the technology. All right, so engineers using secondary data estimated that we get an average reduction of 35% in water use if we could switch the old technologies to the new technologies. That was a monthly reduction in water use. So we went into these communities. We got the billing data from these are community-run water delivery institutions. We approached 1,900 households. We moved commercial folks, and there were a few homes that had multiple, that were on single meters, multiple homes on 1 meter, so we couldn't be sure who was using water. And we approached them and said, would you be interested in having this technology for free? We made 2 visits to every household. We got about 1,350 actually answered the door. And of those, almost 100% said, yeah, I'd be willing to take that technology. And we said, well, we don't have enough technology for everybody. In order to decide whether you get the technology, you got to reach into this bag and pull out a chip. There are 2 out of 3 chips are blue and 1 out of 3 is white. If you get a blue chip, you get the technology. And if you get a white chip, sorry, you won't get the technology. We also did another treatment with among those who got the blue chip, there was another opportunity to get a bonus payment where we said in 4 to 6 months we're going to come back. I mean, we told everybody we're coming back to see how people liked it. But we're going to come back and we're actually going to come into your house and see if you still have the technology. If you're still using it, you'll get this performance bonus of about $20, $25, depending on the exchange rate. And the idea here was to test this idea that if you can induce people to keep using the technology, then they'll persist using it. They won't disadopt later. So the idea is to try to randomly encourage some people to keep using the technology and others you don't, and then see if that random bonus assignment actually predicts disadoption a year, 2 years, 3 years later. This idea that you just need to get used to the technology. So any questions about the design? Right. Yes?
Did you tell them that there was a water-saving technology?
Right, so that's really important. So you see that we knock on the door and we give them the script about the technology. And the script is what they would typically do. It's a water-saving technology. Helps save water for your community, helps save you money. We actually put in there an estimate of how much water you save, which I felt really uncomfortable about, but we wanted to match what would actually happen in a real program where there would be claims about how much money people could save on their water bill, 35%, actually a little bit lower because some of it's fixed, but about 30% on your water bill. But we did that for everybody. That's important because one of the problems is you can't deliver technology about efficiency in the environmental context without talking about why. So the problem is that if we only went to the treated households and said, water conservation is really important in your community, you can save money, and this will reduce your water flow, and we didn't say anything to the control groups, we wouldn't know if I'm measuring the effect of the technology or all that information and salience and priming I gave them about water. So everybody gets that, and we're measuring the incremental effect of the technology itself. Yeah.
I'm interested why you, with the randomization
Yeah.
bit, why you told them that they weren't getting the technology rather than just saying, oh, we'll give you another plastic bit, but it doesn't have the savings.
You mean a false technology, placebo technology?
Yes.
Okay.
Or where you don't know which group
Right.
you're in.
Right. So for 2 reasons. One, for deception. So either we have to tell them that there's possibility of a placebo technology, right? We have to get informed consent. And this was being run by CATIE, which is a Costa Rican NGO. And so there was no informed consent because it was considered a program evaluation. So they would have done deception without telling people, which we were not comfortable with. And the other problem is we didn't know a technology that would be fake but not reduce the flow, because these people often had no pipe at all. So to make something look realistically like it could be a real shower head, but it's actually not restricting flow, we didn't know how to actually do that. So when you look at, but that's why we have some of these behavioral mechanisms are not the actual low flow constriction, but it could be I have this shiny new technology and reminds me about water conservation, and that's why I'm changing my water use. So we're going to try to get at mechanisms. So right now I'm looking at just the average effect, which might happen through all those mechanisms I brought up, as well as some I maybe not even thought about. Yeah.
So 2 questions. One, did you tell people that they were going to be given a drawing to get the technology when you had got the 97% agreeing?
That's a good question. I don't. I'd have to look at the protocol because that's part of the appendix.
It seems really high, and I wonder if like knowing that they were maybe going to get into a lottery was like induced them to want.
Oh,
technology.
yeah. No. So
Doesn't
we were
bias
told by
it.
the Costa Ricans. I was really concerned with. I mean, one reason. So you could go to doors and just offer to some people and not others, but a lot of people are going to refuse, and so you have non-compliance. You have to adjust how you analyze the data as a result of that. So I wanted to get the effect of on people who would accept for free. Right? So not people that you didn't have to pay to get that technology, because that's not necessarily a group that we want to talk about unless we're talking about regulations or standards. But anything voluntary would be the biggest group possible is people who would take it for free if it was installed and everything. So we first asked them if they're interested and then randomized within those groups. I thought we'd get lower. The Costa Ricans said, you're offering them a shiny new faucet for all their faucets that potentially could save them money. Everybody's going to want to do it. They were shocked that 3% said no. And they thought it might be because of the lack of trust. And they were asked, well, who was it? Was it, the woman of the household? And they might be a woman who couldn't make a decision without the male there or something like that. But they thought the opposite. Whereas in the US, we have a hard time getting people to adopt these technologies, even with huge subsidies, right, to do it.
The second question is on the untreated. Are you concerned that they might be kind of
Upset.
ticked off?
Right. So we talked about untestable assumptions and rival explanations in a previous seminar. So even in randomized experiments, you're making assumptions. And one of the assumptions we make is that untreated people don't say, oh, darn it, I didn't get it. I'm going to show these guys. I'm going to conserve water anyway. Right? And then they're no longer representing the counterfactual water use of my treated group had they never had the technology. Or the opposite, I'm going to use a lot of water. That's a little bit tougher because that's individual spite that they're going to incur extra costs to do something that I will never know about. That would be a little bit less likely. But intrinsic motivation to show me, possible. And we're also assuming no interference, that treated groups aren't passing the technology off. The technology is not available locally. It's available in the capital. Could be the control groups drive out to the capital and get their own technology. So we're going to do things like revisit the control households to see if they have the technology. Revisit the control trials and ask them how they felt about the experiment to see if there was any of those concerns. Did they talk among each other? We also mapped out all the households to see if somehow control groups who are next to a treated household are behaving differently from control households who are not next to a treated household because of some kind of communication. So there are these other rival explanations that anybody assumes in a randomized controlled trial. No interference in the units and no effective randomization except through the technology. But it's possible that you get these other effects. So we anticipate those.
If you think about just one more, of like saying the untreated group has the opportunity to get the technology in a year.
So we did tell them that this is a long-term collaboration and that we will be coming back in the future, but we may know, when people ask us, we made no guarantees because we were afraid that there would be some kind of anticipatory effect. That people would know they're going to get this technology and they start changing things in anticipation of getting it. So it's a trade-off there, right? So you want to avoid the randomization bias that they're pissed by saying, well, but you'll be phased in later with, I don't want them anticipating they're going to be phased in later and then changing their behavior now. So that's what we go. And people generally thought it was fair. We're not upset by it. And that's been found in other places, that randomization in low and middle income countries, people actually think it's really, they like it because rarely are things that equally accessible to everybody in the community. The elites aren't getting all the technology and the people down the social ladder don't get it. Okay, so just a couple of things if you're an economist in the audience. I mean, one of the big problems is that like you've maybe seen this study in the United States that they did in Michigan where they randomly encouraged some people to take up energy efficiency and not other people, and they estimated the treatment effect. And the treatment effect was quite much smaller than what the engineers estimate. But it was for only the subgroup of people that were taking up the technology because of the randomized encouragement. We call them compliers. And that's not what engineers are estimating. When they estimate this, they're estimating it for the whole population. Take a randomly selected individual. This is the expected treatment effect of the technology. So by making it so that we got most of the population in through offering it by free, we get as close as possible to what the engineers are estimating. But they might say, but you didn't get those people in who refuse to take it up. So we have to make some assumptions about how do they differ, or we can look at how they observably differ and how they might be different, right? So the engineers say, the reason you didn't get our number is because you didn't force everybody. We're thinking about it as a regulation. Force everybody to do it. This is the average effect. So we try to address with that. We talk about your randomization biases. Is it the randomization procedure itself that's causing everybody to behave unusually? It's not the technology. And then interference among the units, that they talk or share the technology or something like that. And then sampling variability. It's that we have a sample, so engineers are basically assuming it for the whole population. I have a sample from 9 communities in a region of Costa Rica, and the engineers say they're estimating it for all rural areas of Costa Rica. So there might be sampling, just because of our sample, by chance we're getting something different from what they're doing. So we actually had engineers also go in and estimate it for our specific households, not using secondary data as well. But we still have sampling variability that we want to control for. All right, so here's the results. I say preliminary, but they haven't changed. You saw this presentation in May, I think, last year. They haven't changed. This is 4 months after. We also went back in November, so over a year later, 4 months later. I was hoping to have the results for today, but I don't have them. But I've got some disadoption stuff that's interesting. So the first column here is the engineering estimate in cubic meters of water per month reduced. This is how much they estimate, about almost 9. It's a 35% reduction. That's the effect size divided by the standard deviation. It's about almost 2/3 of a standard deviation reduction in water use. Really large. Column 3 is just to show you that who got the treatment doesn't predict past water use, right? If we truly followed our randomization protocol, we wouldn't expect there to be any difference between treatment and control group in their past water use, and there isn't. I should be using the arrows here. And then the experimental estimate. About 2 2/3 meters cubed of water reduced, about a little less than 11% reduction in water use, so about 1/3 of what the engineers estimate. If you can look at the confidence intervals, it's still nowhere near what the engineers estimate in terms of the reduction. And we can look across groups, right? Is there any difference across the heavy water users versus the low water users? Some suggestive differences that you get a bigger reduction for the bigger water users, as you might expect, but we don't have enough power to detect differences across those quantiles. And then we looked at characteristics, their level of education, water scarcity in the community, how engaged these people were in water management. They go to the water association meetings for their local group. None of those things explain variability. So quite homogeneous effects in terms of what we could detect in this sample size. So why don't we get what the engineers got? Why do we get 1/3 of what they got 4 months after the treatment is adopted? I remember these are all the different examples that we gave, all the different mechanisms. So the first one we want to do is simply this. The engineers are basically assuming if it says 5 liters per minute, that's what it does, 5 liters per minute. So we want to go actually measure in the field what the performance of the technology is. And the other thing is engineers are using secondary data. How much water goes to the kitchen sink? How much water goes to the bathroom? How much goes to the shower? Right? What about this communities themselves? How much are they actually using? So we went in, not those 9, but some nearby communities that we could have chosen, but we didn't choose, part of our random group. And we actually put meters on all of their water input. So we could actually measure how much water is going to showering, how much is actually going to sinks, so that we can actually have field measurements from these actual communities. So this is what this is telling us, that we looked at how much water use is coming from showers, kitchens, and sinks for a random sample that we monitor for a week around the same time that we did the treatments. And then we actually looked at the flow, where they actually timed a minute and looked to see how much actually came out of the status quo technology and how much comes out of the new technology that we're installing. And so if we look at the technology as rated, but use the actual data that's coming from the households in terms of how much water they use from these different sources, it's almost 35%. They were quite accurate in their thinking about how much water does a rural Costa Rican household use coming from these different fixtures. When we actually use the true performance rating of the technology, and I forgot to mention this one other thing, in the lab, they open the faucets all the way, right? But people don't open the faucets all the way for everything that they do in the household. So one thing that they also did in these samples is they said they measured the flow with the faucets open all the way, and then they asked people to go up and say, normally when you're at the kitchen sink, show us how you open the faucet. And then they measured the flow from that. When you take that into account, it's actually lower, right? Not by a huge amount, but it's lower in terms of the reduction you'd expect. So taking into account how people actually use water in the field. So when we take into account the actual adoption outcomes, because sometimes you look, there's plumbers, professional plumbers are putting in insulation, but they were cutting pipes. There were some things they looked at that said, how am I going to get this faucet on this thing? It's like a weird shaped pipe. And so they were doing things that weren't necessarily factory installed. And sometimes they actually said, I can't do it at all. Let's not bother. It'd be so expensive to do this. So they actually didn't even install it. But we had data on all that stuff. So when we actually took into account how it was actually adopted and let the engineers readjust their estimate, it dramatically shrunk again. But still about double what the experimental estimate said, about 21%. All right, so we have this enhanced engineering estimate where they actually have data that normally they do not collect. They don't go into the actual houses and look at how they actually use the resource. How does the technology actually perform compared to what it would do in the field under naturally occurring conditions? But if we did that, we'd still be about double what the experimental estimate is. So why? What's going on there? All right, what about disadoption? Right? It may be that we're measuring water use in households that don't even have the technology anymore. They've ripped it out. So on average, about 10% disadoption rate, and it was different depending on whether they had the bonus or not. Those who got no bonus, we had about a 17% disadoption rate at 4 months, full or partial, meaning they took everything out or just some things out. And with the bonus, it was about half that rate. Right? So we have some variation that we're going to use to exploit the longer term data to see if just getting people to use the technology for longer made them more likely to continue using it even when there was no more bonus to be had in the future. And when we try to see who was disadopting it, people said they didn't like the flow in the customer satisfaction surveys. People who were high water users in the pre-treatment period, they had less education, and they were renters versus owners. All right, so that 10.76% is what we call the intent to treat effect, meaning they were randomly assigned to have the technology. Regardless of whether they kept using it or not, what's the treatment effect? But if we adjust our estimates using what's called instrumental variable design to measure the effect on those who kept using the technology, you can't just throw out the people in the treatment group who don't use the technology anymore, the disadopters, because you don't know who they are in the control group because you never can observe that. I see that get done in ecology all the time. You have non-compliance. You throw out the non-compliers in one group, but you're actually left in the other. You've broken the randomization of the experiment. You can't study those two groups anymore, do a comparison. So here we do it appropriately where we're looking at the group of people who are still using the technology because they were randomized into it. And you see a bit of a change. It's a bit of a higher impact. It's 13%. But disadoption is not explaining a big chunk of that difference between the engineering estimate and the experimental estimate. And I do know that we returned in November 2016, a third of the households have gotten rid of the showers, largely because they've been filling up with sediment. And that's something the engineers knew, and everybody got information on how to clean the shower, right? If they get sediment in it, you take it off, you scrub it, and you get that sediment off, scrape it if it's minerals, and just put it back on. And their estimate was it was about a 15-minute operation that they'd have to do once a year. Apparently, these people don't want to do it, right? Engineers assume it's a simple process, everybody will do it. A third of the people just said, forget it, I'm not doing this anymore, and just adopted. In the kitchen faucets, 40% got rid of it. Some of them because they said it broke. I'm not sure, I haven't looked at the data, I don't know if we know why it's breaking. Probably because they use it a lot, and maybe banging pots around and stuff, and because they've got these extended pipes that often come out of the wall, it's really easy to knock the faucet right off or crack it. And they also said sediments. They were just tired of cleaning it and they just threw it off, go back to the old way. The bathroom faucets, much lower disadoption rate. We're going to look into that, but a year and 4 months later, where people generally are no longer measuring outcomes in experiments or non-experimental data, we're seeing really large disadoption and expect that the treatment effects are going to be much smaller. Now, the big question would be, do we get less? Yeah.
So, are the numbers in 3 factoring in the year and 4 months, or are those based on just the 4-month return?
These numbers up here are just the 4-month return.
Okay.
So we have, this is all I know is that we have disadoption, and we go back and look at this. So for people who continue using it for a year at 4 months, what's the effect? Is they still getting the same monthly savings of 12.9%, or are they getting something lower, or are they getting something bigger through some behavioral adjustments? So other reasons, one issue of water in particular is there's some uses of water for which efficiency is not going to affect, like I got to boil beans and rice, I need a pot full of water. It doesn't matter whether it's more efficient technology, it just means I'm going to sit here longer and wait for that water to come out, which could be another reason for disadopting. People didn't say that, but with these surveys, you're asking for self-reported customer satisfaction. Saying it broke or it got clogged up might be more desirable than saying I got tired of waiting for the water to come out. Or maybe that's what they mean by clogged up, is I had to wait for even longer for this thing to go, and I was tired of doing that. If 40% of their water use, which is really high, is for these fixed uses, meaning they couldn't be affected by efficiency, because the engineers didn't take that into account, then the upper bound of that taking into disadoption estimate, that 12.9%, the upper bound of the confidence interval touches what the engineering estimate would be. And if it was 75% or 73.5%, which is totally implausible, that they would equal each other. So in November, we went in with a sample of households. We tried to measure exactly how much water was going to these fixed uses, where they filled up a bucket and they just needed a fixed amount of water. The early stuff that they brought back says it's like 10%. So it might explain part of the difference, but not all of it. But we haven't fully analyzed the data. All right, so the last thing I want to talk about is, okay, at the 4-month period at least, are households leaving cash on the table? Now, the massive disadoption we've seen at a year and 4 months suggests that households are probably not leaving cash on the table. Like even after they're given the technology for free, have an opportunity to use it, they're just throwing it away. They don't want it. So it's hard to believe that these savings, which are 2 to 5 years, is what the engineers assume will be the lifespan of the product. They actually want to say 5, but we also said, let's do it with 2 because of the sediments and other possibilities. That people aren't even holding on to the technology that long to realize some of these gains. We took into account the price and the sales tax. We did the price that we paid for the technology package, right? Not what they would pay in a local market, because the stuff doesn't even exist in the local market. So clearly some businesses decided this is not worth stocking. Another indication that there's probably not cash on the table. Right? So businesses aren't offering this because they think nobody wants it. But it could be because some weird equilibrium, nobody knows about it because nobody supplies it because nobody knows about it, right? So we use a conservative price. We have installation prices depending on whether the people do it themselves or the plumber. We did it with the plumber, but in reality, people will probably often install it themselves, and they have a lower opportunity cost than the plumber. We have annual savings, so we know the prices that they charge in each of these communities. We know exactly how much water people saved on average, so we can actually estimate what people really saved over this time period. And then there's this big question of the discount rates. I don't know if non-economists know what this is, but most people value current benefits and costs higher than they value future benefits and costs. They're not one-to-one translation. Engineers often assume if it costs me $20 and I earn back $4 over 5 years, I've broken even at 5 years. But economists would not assume that. If I have to pay $20 up front to get $20 over 5 years, that's a loss to me because I value those future benefits lower than those current costs. How much lower is a tough thing to do. When engineers do take it into account, they use discount rates of around 6 or 8%, these sort of financial market discount rates. But there's lots of evidence suggesting that people, when they make consumption decisions, have much higher discount rates. They discount the future much higher. So in a complementary study, not in these communities, but at similar communities in that same area, that's 83 that we talked about before, we went in and did state-of-the-art real experiments with real money over different time horizons where they actually had to choose about real amounts of money that were in the same order of magnitude of savings. That we're talking that people looking at $20, $30, $50 payments. Do I want smaller amount sooner or later amount up front? We did risk experiments that you can adjust for risk preferences. And we got households had a median discount rate of 29%. And we also did it for couples, because a lot of these decisions for technologies are couples make them together. And often what they assume is head of household matches what the couple's discount rate was. But we show that the couples are actually far less patient than the individuals were for the same decisions. And we randomized the order, so it wasn't like they weren't making a portfolio or anything. But so we'll be conservative and use the 29% rate. And when we do that and have the technology last for more than 2 years, we get a positive net present value. I mean, there's some gains, but it's never larger than $20, even for the 5-year with the low discount rate, the low installation cost, ignoring the retail price. It's just not that much cash on the table, even making the most plausible assumptions. And if we use the less conservative, we say 44% discount rate, it makes no financial sense at all for people to do this technology. There is no paradox here why people are not adopting this for climate change and drought. It just doesn't make financial sense for people to do that. We do a cost effectiveness analysis and we compare it to some other things that the utilities do to do demand management. Fortunately, their cost data for the other things they do is not as good as the cost data we have for this, so there's extra uncertainty about it. But at 4 months, the utilities thought this was actually pretty cost effective, that they might think of subsidizing this as a way of doing demand management at the community level. But now they see what's happening in November, we heard them saying this maybe it wasn't a good idea to do. And it shows, again, this problem we have in conservation science is not doing these longer term analyses. We often do these projects, measure what's going on, and a year later, it's awesome, people love it, let's scale this up. And not giving some time to see if that shine wears off over time. So the conclusions, do these technologies work in terms of reducing water use? Yes, but far less than the engineers estimate. And longer term effect is pending, but it's going to be even lower than what we estimated before. People leave cash on the table. I say no. My colleague Francisco Alpizar wants to say not a lot. But either way, it's not like people are missing massive amounts of cash on the table. There's a reason why these technologies are not being offered in stores and why nobody has them in their homes. Are societies leaving cash on the table? Should the governments and the local utilities be encouraging these? Pending as we try to make these analyses better. But I think in the longer term results, we're going to see they're probably no worse than a lot of other things they're doing, but a lot of the things they're doing also don't work. Conservation education that they're doing, hiring a half-time plumber to look for leaks. Most of the leaks apparently are happening not near the homes, but underneath the system. It's really hard with their technology to detect those leaks, but we're still working on that. Does the bonus reduce disadoption? It does. And then what we're going to find out from the November data is does experience. So we induced some subgroup of people to use the technology longer because of the bonus. For that subgroup, are they more likely to keep using the technology because they had more experience with it? Now, we don't know for everybody, but that's a causal question that really hasn't been addressed anywhere. So it's at least interesting to do it for this group who would have just adopted had it not been for the bonus. And the bonus is being randomly assigned. So we have a group that would have kept doing it had they got the bonus, but they didn't. And we can compare their water use. And that's it. We've still have a few minutes for questions, but thank you for your attention. Everybody's eyes are still open. That's great. You need a drink? Yeah.
Talk about what's going on in the United States, and is it a function of socioeconomic level? So maybe you have different adoption rates, the high end, low end.
So what drives adoption?
Well, you made the comment that in the U.S., even if you give it to people, they won't use it.
So that's a big question. Now, so this particular experiment that I talked about in Michigan, they were offering about $5,000, I think it was, for $5,000 for doing the actions for an energy audit that suggested for low-income housing. One of the things I think is the problem is that they didn't trust the program at all. It's coming from a community that's low income, they already have low trust, and then the outsiders show up and they're just going to give me money that covers a lot of the cost of doing this miraculous thing that's going to save me extra money. That sounds too good to be true, but that's just my speculation. So there was a study I told some people about in England where they were trying to get people to insulate their attic. And they were giving incentives and no one was taking up the incentives. And some people did some qualitative research that suggests that people just thought it was just a serious hassle because the attic was filled with junk. And so they did a randomized experiment where some people randomly offered this service. That was a real commercial service that they would come to your house, take everything out of your attic, put it on your front lawn. You could decide what things you wanted to come back, what things you wanted to donate. And while they were doing that, the insulation company would go in and do the insulation. So there was just like a coordinating. So the people still had to pay for the insulation and the attic cleaning service, but the experimenters provided this sort of reduced the transaction cost. And economists would say that's not going to have any effect because those businesses already exist. If I actually wanted to do it, I'd call. I mean, it's 2 phone calls. How hard is that to get them to come on the same day? If the experimenter can do it, I can do it. But what they found is installation rates went up for those who were randomly offered that opportunity than those who wouldn't. So didn't have to pay them any subsidies. You just had to give them this way of reducing the complexity involved with putting in the attic installation. So there's lots of theories on why people don't adopt it. The classic one a lot of economists say is because it's not financially worth it. I mean, I did it with my own house. I got an energy audit. And they were trying to sell me things like isolene or something like that, insulation, the foam insulation in my attic. I had like an 1,800 square foot home. And when I did the calculations, it was going to be like a 15-year payback period at a discount rate of 6 or 7%. And my discount rate might be that low. But it just didn't make any financial sense to do it, even though they claimed it would. So I think that could be a big reason, is not as financially profitable as people say, but there could be these behavioral quirks that are awesome. People argue it's present bias. If you create a funding mechanism that sort of front loads some of the gains they'd get, right? So people do this for businesses now where some third party comes in and says, I'll pay for the installation and over time you'll pay me back some of the gains from the savings. And then people are more willing to do that because their costs are not front loaded, they're spread out over time. Yep.
I was thinking about gender as you talked about this, and I wonder if you have any, I know it wasn't your central focus, but I wonder if you have any observations, because there's a sort of an incentive structure problem because you're working at the wrong unit of analysis when you work at the household.
Right.
If you're dealing with a situation where there's an internal gendered division of labor or internally gendered balance of power, both in terms of who manages money and who uses water, a lot of these programs, they'll be talking to the guy standing out in front of the house, but the principal beneficiaries of water conservation might be women and girls and all that kind of stuff. So I'm just curious if you have any observations about whether gender creates those kinds of labor and power divisions such that the household's not always the right level of analysis, or maybe part of the explanation for why.
Certainly on the technology adoption side, that's right. On the use side, I mean, everybody uses water in the house, so that's the relevant unit if we want to find out what the effect is. But if you're thinking about different technologies, might have different effects depending on, what's going on in gender issues in the household, and certainly adoption. Right? So we actually talked about trying to randomize who we asked, whether it be the male head of household or the female, but then we realized logistically it was going to be too difficult to do that. That for other contexts, that might be irrelevant, or whether they're both there when you do it or not both there when you ask them. Broadly, when we did the stuff on time and risk, we did ask them questions about other climate change adaptation investments, like a water tank. We asked them separately, do you make this decision yourself or do you do it as a couple? And we found in that context that most of the key technologies or practices we were looking at self-reported it was the couple makes the decision. That's why we were more interested in the couple discount rate, because then if they're making a joint decision, that's the relevant one to use. And unfortunately, in this context, it makes it less likely that they'll adopt things that would help them, according to scientists, adapt to climate change in that area, because they're more impatient when they make decisions jointly than individually. But I think that's right. Just showing that couples and individuals make decisions differently. I don't remember the Maria who worked on the risk and time stuff. I think she found gender differences in discount rate and risk, but I don't remember the direction of them. But certainly that makes a difference. Good question over here, Joe.
So I'm just curious, as far as, funding more of this kind of research, like randomized control trials in social sciences.
Right.
Is there a lot of interest, or is there sometimes sort of a problem that, like, when a government puts out a program, they actually don't want to hear that it's only a third as effective as, they want to be able to kind of
Just
tout
do it,
these
yeah.
benefits, and engineers
Yeah.
also maybe don't want people to come in and say their technologies don't
Right.
work in reality.
Yeah. So, I mean, so luckily this idea came from Cartier and scientists. So the people at the local level, they didn't care if it worked or not. It was not going to cost them anything. But if they came up with the idea, or the government agency came up with the idea of actually doing this, then it's a lot harder, because you're asking them to say, here's your great idea. I'm going to compare it to your great idea never existing at all. Let's see which world seems to be better. That's hard for someone to put themselves out there. I mean, none of us want to know whether our organizations would be better or worse or the same if we never existed, right? That's not an experiment any of us want to see the results of, even if you could do it. So it's easier to do it when the idea comes from the outside and people whose jobs don't depend upon it, their egos are not tied into that innovation, or in which cases they are, you do a horse race between two different variations of the intervention. So that way, if you find no difference, you can't say the intervention doesn't work. You can just say that the two variations have no effect. So you might have an idea of, we go in and we talk to whoever answers the door, or we have a variation of the program where we make a specific effort to get to the woman and get talking to her for adoption. And we test those two approaches and see what the impacts are of those two variations. It's a lot safer for a government or NGO to do that, because maybe they'll find out that doing one is actually better. And if they don't, it's still, nobody can say the program's not a good program. So it's not great for scholars. We want to know, does the program work? But it's a way to get some movement on the evidence base. And then sometimes these variations that we do actually lead to changes in participation, like the performance bonus, that we can use to get at the causal effect of the program itself for some subgroup. So with USDA, we did a program that varied the participation in one of their programs. All the government cared about is trying to induce participation, higher participation. But now we have some people participating. The only reason they're participating is because they randomly assign different outreach. And so we can use that as an instrumental variable to try to figure out the effect of the program on that subgroup who would never be participating if they didn't get that particular form of outreach. Yeah.
So what you've described with water it reminds me of what our experience is with lawns, comparing what sort of the agronomists think is right fertilizer application versus when you go and you look at what people are actually doing, it's way lower than what the agronomists are saying is the amount of fertilizer
way lower, yeah.
It's
because usually it's the opposite, as agronomists often assume that people over-apply. And then if we give them more information or precision agriculture, they'll do less. In that case, they might have the opposite effect if you told them that,
It's completely reversed. No one's applying that much fertilizer.
In Baltimore.
Well, in our 6-city study, that's what we're
6
finding.
cities.
Yeah, part of it's people are lazy, but part of it's also they don't apply as much as what's recommended.
Right.
But I guess I wonder, like, what is, when you go back to these engineers, or we go back to our agronomists, like, what is a reaction to understand the human dimensions of this? That it's not it's not acting like they think it acts.
Right. So their response in Costa Rica, and even some people in the department, is, oh, that's good to know. Now we can just put a fudge factor into our model. We'd reduce it by half, right? Because they said, well, we do the enhanced estimate or reduce it by a third. I said, well, this is like one sample. I wouldn't, we need more of these tests. You need to understand the mechanisms, because different programs have different effects. But their initial reaction was, this is good to know. And now we can adjust our model calibration to take that into account. Now behavioral response is a thing. It's a line in their model. Now to adjust by 2/3 for the behavioral response.
Okay.
which is not ideal, I don't think.
It's not insight, it's just, they just want a factor.
Yeah, they want a factor, right?
Would you care to reflect on, I mean, one of the things that made this possible is that this technology is cheap.
Right.
And
You mean it possible we could afford to do it as an experiment on our
yeah,
own?
and if there's a correlation
Yeah.
between the cheapness of the intervention and the upside.
Oh, yeah?
Just, yeah, maybe interpreting this lesson for bigger things
Yeah.
is tough, right?
It's
And-
tough. I mean, all we wanted to do is say, here, this is analogous to lots of situations. Let's see what's happening here. But there's no reason, just like I think there's no reason to believe that the effect of this technology on water use would be the same across different sorts of programs, information versus standards. It wouldn't be necessarily the same for farmers adopting irrigation efficiency technology for water, much less energy efficiency, fuel efficiency, businesses adopting it for large-scale manufacturing. And so, it comes down to, again, a lot of times the manufacturer, they argue that there won't be any behavioral change. I find that hard to believe. Businesses always say, I got a new technology, now I can do things differently. And it's you need to have some more studies, but the theory is really important. Think about the mechanisms, because you can't do a study in every context, but certainly more than one would be useful. This one seems pretty straightforward and doesn't seem to allow for a huge amount of behavioral changes. I mean, yeah, you could change the length of your shower, but you're really going to change it that much? There is some evidence that they changed the length of washing dishes. They made it longer because the force isn't as high, so it doesn't knock the stuff off the plates as easily, so they got to wash for longer. We don't have any quantitative measures, but it's just sort of self-report.
I don't know how common it is, but in the U.S., a lot of policies require, like we put in geothermal power. Right. Huge outlay initially, even though you get most of it back in tax credits, but that's got to be a huge disincentive for a lot of people.
Sure,
You
yeah.
have to be educated enough to figure out what the tax laws are, and you
I looked into it because a neighbor of mine did it, and he said, this is going to be great. And I said, it is not going to be great. And 5 years later, he said, this is not great. And it wasn't just the fact that the payback period was nothing like he thought, but the other problem was he didn't realize how costly it was, that the marketing material way underestimated the maintenance costs, how frequently things break. It's like compact fluorescent light bulbs last up to 7 years. Maybe in a lab they do, but I've never had one in my household last anything close to that. So that could be another thing with geothermal, is that people rightly look at it and say, I don't know enough about the maintenance costs over time, and they hesitate. And it could be that they're wrong, and more experience from social leaders and neighbors will actually induce them to adopt it, or it could be the opposite, like this guy in my old neighborhood, nobody was going to adopt it based on his experience because it just became too troublesome to maintain it in his home. He still was proud of it. He showed everybody come into the household. It was a great signal of his identity, but in retrospect, it wasn't that valuable.
We've not had any trouble with ours. For the record.
Could be differences in geography, right, where you put it in and who puts it in. All right, thanks for your time.
Thank
Thanks.
you.